Today I'm going to be going over a topic that most people really despise and hate, and I was one of these people. And this topic is vectors, which seem to cause a lot of trouble for almost every student that I know inside our school and outside. They have at some point struggled with vectors, so I'm going to be going over the general way that vectors can be used in the entire mechanics textbook. So this video isn't specifically to one chapter, it's sort of how vectors are applied in each and every chapter. The first thing we need to know is the very definition of vector. So I'm going to go over the basics quickly of what vectors are, and then I'm going to basically apply them and see why are they useful in any of the problems of the mechanics textbook, and hopefully that gives you a view of how to use the vectors in the future. The first thing is that in not only physics but all of maths we can define different values that we know but by either saying that they're scalar or vector values. Scalar values simply have an amount. For example, time is scalar because it's just some amount that's passing by. But vectors also have direction. So we can have the magnitude of a vector, which is the amount that it is, but we can also care about which direction this force is acting. So let's say, for example, imagine we have this person, and let's say this person travels 100 meters in this direction, so let's say to the east. And then, once they travel those 100 meters, they decide to travel 100 meters to the west. Now, east and west are opposites, which means that this person has traveled 100 meters one way and 100 meters the other way. The distance that this person has traveled is a scalar value, which represents how far were they moving in total. So here we can see that they've moved 100 meters firstly, and then they moved another 100 meters. So this person has traveled a total of 200 meters based on their distance. But we can also use the vector value of distance, which is called displacement, to measure how far they've traveled from their starting point. So because we're fixing their starting point here, and we're using that as a measure of value, we care about how far he is from the starting point, so it depends on which way he moves. He moved 100 meters away from his starting point, but then he moved 100 meters in the opposite direction, which means he moved 100 meters back. So actually, if we use direction to measure how far this person has traveled, we can say that they have traveled no distance, a total of 0 meters, because they ended up where they started. So what we can say is that we can say moving east counts as adding a positive amount in the direction that the person's moving, and moving west would be a negative amount because it's the opposite direction, and the opposite we can say is just a negative version. So if we were to add the displacement now that this person has traveled, we get 100 minus 100 is 0 meters. So this person has traveled no distance. And that's what vectors do. Vectors are useful in the sense that we can use them to figure out more information about something instead of just its value. Even though the value can be useful for some things, but if you're doing physics and you have vectors, things are going to be moving in different directions, and that does matter, because depending on what's happening, different things will change. Imagine we have a block. So what I'm going to do is I'm going to look at the different forces that this block has, because a force is a type of vector quantity. Force cares about the direction that things are happening. For example, imagine that you and your friend are pushing a block. Now you guys want to work together to make the block push further. Each of you can apply 20 newtons of force towards the block to help push it. That's great because that means that you can work together to push the block easier and further in less time. But the direction that you guys are pushing does matter. If you and your friend work together to push a block, but one of you is pushing in one direction and the other person's pushing in the other direction, we know, just like if you were to do this in real life, that the block wouldn't move because you're opposing each other, you're fighting against each other. And this is true because forces care about the direction that things are moving. So if there's a force of 20 newtons going one way and a force of 20 going the other way, then the block is not going to move, because it's going to have a total of 0 newtons in neither direction. Since these are opposite, when we add them, we can say that one of these will be negative and the other is positive because they're in opposite directions. So then when we do 20 plus minus 20, we're going to end up with a net or total force of 0. How can you and your friend work together to actually push the block? Well, if you think about it logically, what would you do to work together to push the block? What you would do is just, well, push in the same direction. If you and your friend work together to push in the same direction, then the block will start to move. And this is true because the forces are acting in the same direction now, which is what vectors care about. So then we can add these two vectors together. 20 plus 20 will be 40. So the block will be pushed by 40 newtons of force. In this way, we can see why the direction of vectors matters. And this helps us to get a better understanding of why we need them later on. So let's look at an example and try to understand when will vectors act in which direction and how do we know and how will we be able to find out in the exam. Let's start with understanding how vectors can be made. So what we have here is a diagram and we have a particle P. What I'm going to do is I'm going to start pulling particle P in one direction using a force and pulling particle P in another direction using another force. Over here I have two forces that are acting on the particle. But let's imagine that I now want to add another force, so I pull it in another direction and this causes the particle P to stay and not move. This means that all the forces pulling in each direction have to be evened out so that in total there will be zero force. Similar to how our one friend was pushing one way and we were pushing the other way. But how can we do this? How do we know which way the force has to go? Well, the first thing we have to do is we have to write these forces into their separate parts. What does this mean? Well, these forces are all acting in completely different directions, and it's a little bit difficult to understand how they're related. In the previous example, both me and my friend were pushing on the same sort of direction, but one was pushing one way and the other was pushing another way. But now these forces are acting in complete random directions, so we don't know which way what is moving. But we can do this by splitting it into two parts. Imagine I were to make a triangle out of this force, connecting from here to here. We can see that this force, this vector that is acting this way, can be written as two other vectors. These can be a vector that's moving horizontally and one that moves vertically. I like to say that this is sort of like taking another path, because vectors care about the direction. It's as if you're moving from one point to another. And instead of going directly that way, we take a separate path which goes along one side and then along another side. Now the issue with the original vector that I gave is I didn't give enough information. We have a vector here, 10, but that's only a magnitude, an amount of the vector. But I can also tell you which direction it's moving, because we can see here that the vectors are moving in different directions. So for example, you might know, or they might tell you in the exam, that between the horizontal direction and this vector, it's about 37 degrees. Now what's helpful about this is that we want to split the vector into two parts, one which is horizontal and one which is vertical. And what we've made here is a right angled triangle. So what we can do is we can use our trigonometry skills from pure maths to figure out what these horizontal and vertical vectors would be. So because this vector has a magnitude, an amount of 10, we can say that this length is 10 newtons. So then we can find out using our trigonometry what the other two lengths will be. So using my trigonometry, I find out that this horizontal component is 8 newtons and the vertical component is 6 newtons. Now you might be wondering, why are we doing this? Well, what's cool is we can also do this with the other vector. If we're given the angle, which I didn't include here, but you would, or you'd be given something else to help you work with, you could create a triangle for this vector too. And then you could deconstruct it into these two parts of horizontal and vertical. So if I were to use my trigonometry again for this vector this time, and I were to tell myself this were, for example, 53 degrees, I could find out that the horizontal part will be 9 and the vertical part will be 12. So now what I've done is I've split these two vectors, which had completely different directions, into two parts where they share those different parts. Both of these vectors are now made up of directions which are parallel and perpendicular to each other. In mechanics and in other areas of math, we can write this as in a certain type of notation. We call this the IJ notation. The IJ notation is a very handy way to write out your different vectors because it splits them into components that we can compare and add together or subtract together. So, for example, this 10 Newton force, which was at 37 degrees to this horizontal axis, can be written as 8I, where I just means a horizontal vector that moves this way, and 6J, which is our vertical vector. So this is, in a way, you can think of your x and y graph, where you have the x value and the y value. So what we end up here is we're moving 8 horizontally and 6 vertically. That's all this means. We can also write the other force of 15 newtons in IJ notation. But just like a graph of x and y, and like we said, vectors, they care about the direction. So because we have this j component that's also going up, we're going to say that up is positive. So we're going to have a vertical component of 12j, which is in the positive direction. But because the horizontal component is going to the left, it's going to be negative because it's going the opposite direction or the negative direction. So what we like to say is that to the left is negative, to the down is also negative, and then up and right are both positive, just like in our x and y graph. So now we've taken a completely random number, just an amount that we had 15 newtons, and written it in an even more useful form of vertical and horizontal components, which help us to understand the vector more. So now I can rewrite my vectors on the graph using this IJ notation. Now what we can do is we can combine the vectors just like we did with the block and the person. We had them pushing in opposite directions, and we found out in total what's the force acting on the block. Well, it would be 20 minus 20, which gave us 0. Or if they were pushing in the same direction, it would be 20 plus 20, which gave us 40. So let's add these vectors together too. And we're going to add the horizontal parts together and then the vertical parts together to get a new vector. If we look at the horizontal vectors, which is our I parts, we see that minus 9i plus the 8i of the other vector gives us minus I, or minus 1i. And that would be the horizontal component of the vector. So if one person is pulling it with minus 9 newtons force in one way and the other's pulling plus 8 in the other way, it's going to move minus 1 in one direction. Now if we look at the vertical components, which are our j vectors, because they're both acting upwards, they're going to support each other and work together, just like you and your friend pushing the block in the same direction. So we will add them together. 12j plus 6j will be an 18j vector value. So what we call the resultant force, the total force, will be minus I plus 18j newtons. And this is our total vector when we combine those two. It's important to note that I and j are not variables that you can solve. All they mean is left, right, up, and down. So they are not variables that you have to find the values of. We just use them to represent the directions that we're moving. Now, if we consider this resultant force that we have, we can think, if this is the total force that's being added to the system, what would be the force that I would need to add to make the total force equal 0? Well, that would be a force that we need that would make this move 0 in any direction, so 0i and 0j. How do I get from minus 1i to 0i? Well, I add 1. And how do I get rid of going 18j upwards? Well, I go 18j downwards, which is negative 18j. And this would be the opposing vector that we could add to make this particle not move at all. So if you add a force that moves exactly in this direction, then the particle will stay stationary. And we can see that these two are opposites of each other because this is the negative version of this and vice versa. So they act in complete opposite directions. There's one more thing I'd like to note, is that if you are given your IJ notation in the exam, you can use this notation to find out the force and the angle that the vector is acting at. We usually measure the angle based on the horizontal I direction, but they might sometimes ask you different ones, so look out in your exam. But all you would have to do is use your trigonometry and or Pythagoras' theorem. Because, like we said before, this is basically a right angle triangle where we split it into two vectors of 8 and 6. We can use Pythagoras to find this long end, which would be the vector itself, and that gives you the magnitude. If I have a vector v, and I wanted to find its magnitude, I would take the different components, the horizontal component, the I1. Of course, you don't need to write I or j, they aren't real values. So I would write whatever the number of I is squared plus whatever the number of j is squared. So 8 squared plus 6 squared. And of course then you square root that using your Pythagoras to find out that you have this value as 10 newtons, just like we started with. Now, when we want to find the magnitude of vectors, sometimes we will write it like this. We put two horizontal lines around the vector v, and that represents the magnitude of the vector, so the actual value. We can also find the angle of this triangle using our trigonometry, for example, the tan ratio, and then that could give you the angle. If I were to do that for this one, I could end up getting this angle. And if they, for example, asked me to measure it from the positive direction, I would just, because this full length is 180 degrees, I could do 180 minus this angle, and that would give me this part, which would be the angle to the positive I direction, which is usually where we measure our angles from for vectors. But then, like I said earlier, they might ask you different ones, so you just have to measure it to those sides. So that is a quick rundown of how vectors work in mechanics, and I hope that you guys understood a bit and you learned about why the different components are important because of how we can relate them better than vectors acting in all random directions, and maybe even try to see how vectors can be used in different exam questions for mechanics. But I hope that this was helpful. If you guys have any questions, feel free to ask, and have a nice day. Goodbye.